Number 1, create DNA cleavage assay protocol. Determine the correct reagent volumes in the DNA cleavage assay table. Let's view the assay table. Now that you have designed a DNA cleavage assay, you must create an experimental protocol by determining the correct volume for each reagent you selected. Type the correct volume in the boxes below. The total volume is 50 microliters. If you get stuck, use the hints. Number 1. The reagent is 10x DNA cleavage buffer, and the concentration before dilution is 10x stock solution, and the concentration after dilution is 1x. So to determine the volume of this buffer, we have to divide the 10x and 1x to multiply it to 50 so that we can get the answer of volume 5.
So for the reagent of CCR5 DNA, we have reagent concentration before dilution is 100 nanogram microliter, and concentration amount after dilution is 300 nanogram and doesn't have dilution factor. So now we compute for the volume of CCR5 DNA 300 nanogram times microliter divided by 100 nanogram, then cancellations of nanogram, we have the volume of 3 microliter for CCR5 DNA.
So for the Cas9 protein, we have another method if we don't know the dilution factor. So we have the given of 5 micromolar and 500 nanomolar. So first, we must convert the 500 nanomolar to micromolar, in which 1 micromolar is equals to 1,000 nanomolar. So 500 nanomolar times 1 micromolar over 1,000 nanomolar, we cancel the nanomolar in 500 and 1,000. So times 500 times 1 micromolar divide 1,000 nanomolar is equals to 0.5 micromolar. We will divide now the 0.5 micromolar into the given of 5 micromolar, in which 0.5 micromolar divide 5 micromolar is equals to 1:10, in which this is our dilution factor. So yung 1 micromolar is equals to 1 microliter, in which gagamitin natin for the volume. So 1:10 times 50, yung total volume, is equals to 5 micromolar or 5 microliter.
So we have 10 micromolar and 500 nanomolar. First, we get the 500 nanomolar times 1 micromolar divided by 1,000 nanomolar. Let's cancel the nanomolar. We have the 500 divided by 1,000 is equals to 0.5 micromolar. And now, after getting the 0.5 micromolar, we divide it to 10 micromolar equals to 1:20 dilution factor. So that the 1:20 dilution factor times 50 is equals to 2.5 micromolar or 2.5 microliters.
For the water, add all the volume in reagents. 5 plus 3 plus 5 plus 2.5 equals 15.5 microliter, and then minus lang yung 15.5 microliter sa 50 total volume equals 34.5 microliter.
In conclusion, the RNA and DNA experiment in nursing education aim to elucidate their differences, stressing the importance of grasping their unique features. The simulation tasked students with defining RNA, distinguishing it from DNA, understanding RNA functions, and exploring its clinical relevance in nursing. This hands on approach enables students to integrate theoretical knowledge with practical skills, enhancing their comprehensions of molecular concepts crucial in healthcare. The experiment underscores the value of laboratory simulations in nursing education offering practical insights into molecular biology and equipping students with the skills applicable in clinical settings. Emphasizing proper controls in the experiment highlights the necessity of maintaining a controlled environment, a skill essential for accurate experimentation in healthcare practice. Additionally, the experiment brings attention to the fragility of RNA, emphasizing the importance of meticulous handling, a critical aspect of preserving biological materials in clinical settings. This knowledge prepares future nurses to handle diagnostic assays, ensuring accurate results and bridging the gap between theory and practical application in their clinical roles. Laboratory simulations hold vital importance in replicating real-world scenarios, offering a controlled setting to gauge molecular activity. The choice of proper controls becomes imperative to ensure unbiased results in a reliable assessment of gRNA efficacy. This involves maintaining the stability of the gRNAs by storing them in a freezer or on ice during the DNA cleavage assay design. Acknowledging the chemical fragility of RNA in comparison to DNA, the data generated from this simulation will serve as a critical purpose, determining the volume of reagents required for optimal results. As RNA is chemically less stable, understanding the impact of temperature on its integrity becomes crucial for the success of the experiment. By utilizing the gathered data, students can fine-tune the experimental conditions, ensuring accurate measurements and reliable outcomes. In the context of this distance learning activity, this simulation provides understanding to students with a practical understanding of RNA, allowing them to differentiate it from DNA and comprehend its functions. Moreover, the exploration of gRNA efficacy offers insight into the clinical relevance of RNA and nursing practice, fostering a deeper understanding of molecular application in the medical field.